In a typical publishing organization, authors need to send documents to others for review. These reviewers send back feedback either in the form of revisions or comments. We could rely on the revision tracking capabilities of Word, but sometimes this isn't good enough. Document protection, in other words, where you set a password that the user must provide if they want to change the document, it's not a security feature, it's a user interface feature. A document that we send to a reviewer might be edited in a document editor, in other words, in an Office suite that made changes without noting tracked revisions. We need to know in a publishing system, when we get this document back from the reviewer, exactly and precisely what is changed. Sometimes there are legal or political ramifications, and if we don't note certain changes in the document, then the reviewer might have cause to feel upset, or there may even be other ramifications beyond that. It would be useful to be able to take two docx files and understand precisely whether they have exactly the same content, and if they don't have the same content, we want to know what are the precise differences between them. To these ends, I embarked on a project to build a new module for WmlComparer Tools. This module is WmlComparer, and it compares two documents and reports the revisions in those documents. Now, Word itself has this type of functionality. You can compare two documents in Word, and that feature works very well. However, we want to integrate this functionality in the middle of a workflow, perhaps on SharePoint or some other content management system, and we want to be able to determine the revisions without invoking Word or using Word. That's a pretty bad architectural decision with regards to reliability. So we're comparing the contents of two documents. What is content in an OpenXML document? The way I've defined content in an OpenXML document with regards to comparing the contents is that if you can select that content in the main document story of a document, then that is content. So, for instance, of course, this text is content. I can select it. This image is also content. I can select this image. Some things that are not content. Bookmarks are not content. We can't select bookmarks. And it's not really relevant in the process of sending documents to reviewers and back to need to see what bookmarks that reviewer has put into the document, if any. There are other pieces of content such as math formulas or smart art. Anything that's in the main document story is content in the sense that we're thinking of content in this particular screencast and when we're talking about the WmlComparer module. One note about the WmlComparer module is it does not compare styling. It only compares the content. We simply want to know, did the actual content of the document change? We're not so concerned about whether that reviewer happened to change a style on a paragraph either intentionally or inadvertently. The algorithm for determining differences in content has been known for years. It's called the longest common subsequence algorithm. You can read about this algorithm on Wikipedia if you like, but in effect, just to simply say the name of the algorithm implies almost the entire algorithm. The gist of the algorithm is to take two documents and you find the longest sequence of content that is common between those two documents, and you set that as a status of equal, and then You can then either determine other content has been inserted, you can determine other content has been deleted, or in some cases, after finding inserted or deleted or equal content, there's other content that we still don't know about. So this algorithm is an iterative algorithm. It takes some unknown content that is correlated to each other, finds equal content, finds inserted content, finds deleted content, or notes other smaller regions as unknown, and then it runs the algorithm again until we get to the point where there are no unknown correlated regions in that document. When I took on this project, my first thought was, how hard can this be? It's a pretty simple algorithm, a little bit of data structure, a little bit of iterative code. You can code this algorithm for a text file in an afternoon. But as it turns out, we can't think about word processing ML in the same way as we think about a text file. There are effectively two types of content in a word processing ML document. There are paragraphs that have text, and then there are tables that have rows, that have cells, that have paragraphs that have text, and those cells could in fact also contain nested tables. As it turns out, this was harder than I thought it would be, but I think that in the end I came up with a good solution. At least the solution that I came up with makes sense to me, and I like the output of the algorithm. The remainder of this video explains the algorithm in detail. I'm going to warn you that I'm going to get very nitty-gritty in this screencast and talk about classes and class hierarchies and recursive functional transforms and so on. I'm going to just blaze through this technical detail. This is a 400 level screencast. From this point on, I recommend that you watch this screencast only if you are interested very specifically in this algorithm. For instance, you might need to implement this algorithm on a different platform than C# and when using the OpenXML SDK. If you want an overview of how to use WmlComparer, then you can find that information at this screencast. As I mentioned, this algorithm is not a pure functional transform. It's an iterative algorithm where it goes into the document, it finds correlated sequences of content, it notes them, and then notes inserted content, notes deleted content, and then iteratively does this until there are no unknown correlated sequences. While this algorithm is not written in the pure functional style, there are many places in this algorithm that uses pure functional code in local scope. I'll point those out when we get into this code in detail. One of these places is pretty interesting. It's a recursive pure functional transform that has a pattern different from the normal pattern of writing RPFT. I'll discuss that at some point in this video. Let's talk about an issue that relates to older code in OpenXML Power Tools. In the OpenXML regex module, I took an approach of splitting runs up into runs of a single character, and this enables us to better parse and look at the text in a paragraph or throughout the document. However, there was a constraint with that approach, which is it takes a lot of memory. We don't have enough memory to split up the entire document into runs of a single character. Well, we actually have enough memory, but allocating that much memory causes performance issues such that it becomes unwieldy, unmanageable. We can't take that approach due to performance reasons. This WmlComparer module takes a different approach. It builds up a data structure that represents the entire document, and this data structure is at the character level, and it points back into the original XML tree so that we can keep track of what parent elements a particular character is in. This allows us to build up a data structure for the entire document so that we can treat the entire document at the character level, doing appropriate comparisons, looking at each character to compare it to other characters. And then at the end of the process, it takes this data structure and builds the complete open XML tree for the main document part again. There are characteristics of this algorithm that enable us to do this. Here we're looking at the WmlComparer module. Let's look at some code. Here is the compare method. This is the public method that you call when you want to compare two documents. The first thing that this module does is it looks for invalid content, and if you are trying to compare a document that contains invalid content or content that's not allowed for this algorithm, then this will throw an exception. These are things such as alt chunk content, sub document content, and content part content. We're not going to process any of that type of sub content. This isn't the normal workflow anyway, but we're not going to handle that, so we better throw an exception if we see it. The next thing that this module does is it removes existing OpenXML Tools markup. This module will put some additional markup into the document that we can use to assess the document later on. So in order to enable running this on a document that we've already processed with this module, we remove that existing markup. The next thing that this module does is it uses the markup simplifier to simplify the markup of those documents. It does things such as remove bookmarks, accept revisions, remove comments, remove content controls, and so on. The content that we are removing when we use markup simplifier is not considered content as far as this algorithm is concerned. The next thing that this module does is it goes into every piece of block level content, including paragraphs, including tables, rows, and cells, and it calculates an SHA-1 hash for that content. This enables us to compare two paragraphs to each other and see if the contents of that paragraph have changed just by looking at the SHA-1 hash. This is a key part of this algorithm. It's critical to making this algorithm work. The next thing that this algorithm does is it creates a list of all of the atomic pieces of content. In other words, these are the smallest pieces of content in each of these documents. Let's take a look at what this content atom list looks like. I'll write just a teeny bit of code so that we can look at this. I'm going to use a little method that's in OpenXML Tools called testutil.notepad, and what this does is when it reaches this point in the algorithm, it will take this string and throw it up in the Notepad editor. That's a convenient way to look at fairly massive multi-line text in the Visual Studio debugging environment. I'll set a breakpoint right here. I'm going to compare two documents, CA001-plain and CA001-plain-mod.docx. These are in the test files for OpenXML Tools. Let's look at those documents. We can see that the only difference between these two documents is the word provides has been deleted. Let's run this algorithm on these two documents. And it threw up Notepad++ with the text of those two documents. We can see here is a content atom list that contains video provides a powerful way to prove your point, followed by the paragraph properties, which signals the Pilcrow mark or signals the end of the paragraph. You'll notice here that the Visual Studio debugger is still running. It'll run until I actually close Notepad++, at which point the testutil.notepad method returns and we hit the following breakpoint. The next thing that this algorithm does is it converts that data structure to a different data structure that has hierarchy. Let's talk about classes and class hierarchy for a minute. There is an abstract base class called comparison unit. This comparison unit contains a list of its children comparison units in this contents field. It contains the SHA1 hash for this comparison unit, and we can look at this hash and compare it to a hash of another comparison unit to see if they are the same. It also contains the correlation status, whether this content has been inserted, deleted, or is equivalent. And we'll discuss how that comes into this algorithm here in a bit. There are three descendant classes of comparison unit. We've already seen a list of comparison unit atoms. This is the smallest piece of content in the document. In addition to the comparison unit atom, there is also a class comparison unit word, and this will contain a list of atoms that make up a single word because we want to find revisions in the document at the granularity of a word, not the granularity of a character. So in order to facilitate that functionality, we group together all of the atoms into a word that we will actually compare and determine differences between. So a comparison unit atom is a character, an image, a symbol, and so on. One point about this is in this algorithm, a math formula is also a comparison unit atom. I didn't attempt to figure out what are the precise differences between two math formulas. If they change, then this algorithm simply notes the previous math formula as deleted and the new math formula as inserted. It would be a different and interesting project to do the comparison inside the math formulas, but that isn't the key point that we're discussing and solving with WmlComparer. We really want to just determine if the text of the document, if the actual sense of the document has changed. We want to know whether a math formula has changed. We just don't care how it changed. We just want to know that it did change. Another thing that I did in this algorithm is I also didn't attempt to dig into smart art and determine what has changed within the smart art. It simply notes if the smart art has changed, it notes that the smart art was deleted and then inserted. There is one more class that derives from comparison unit, and this is the class comparison unit group. Comparison unit group is how we deal with such things as tables, rows, and cells. There will be a group for an entire table. There will be a group within that table for each row. There will be a group for each cell within each row. And then, of course, within that cell, we would find a group for each paragraph. And then within that paragraph comparison unit, we would find the list of word comparison units. Within each word comparison unit, we would find a list of each atom. If we look at comparison unit group type, we can see that the 4 types of groups are paragraph, table, row, and cell. The reason we need to group information before running the LCS algorithm, in other words, the longest common subsequence algorithm, is that we don't ever want to match up contents in one cell with contents in another cell. We want to treat each cell as an individual unit, find the deltas in that cell. We don't want to set text in 2 different cells as equivalent if it happens to be per the algorithm. We never want to find that. Text is only equivalent within the same cell. The comparison unit group functionality is an essential part of the algorithm, for instance, that determines that a row in a table has been deleted or inserted. I've now removed that other debugging code that I just added, and I've added some new debugging code so that we can see what this hierarchical version of the comparison unit list is. This is what's returned by this method getComparisonUnitList. I press F5 and it opens up Notepad++ and dumps out this comparison unit list. We can look through this list. We can see, yes, we in fact have a group with a type of paragraph. We have a bunch of words, and within each word we have a number of atoms. Everything here has SHA-1 hashes so that we can look at them and determine whether that content is equivalent to another piece of content as we need to per the algorithm. I'm going to stop debugging for a second and clean up this debugging code that I've added into there. In order to reassemble the original document or the document with modifications after we get done with it, this algorithm annotates every single element with a GUID identifier. This means that we can see the start of the GUID identifier right here. We can see that all of these paragraphs are part of the same paragraph and all of these runs are part of the same run. Let's digress from this example for just a minute and look at an example that includes a table, and that will be interesting to look at this comparison unit in that context. Here's a test where the after document contains a deleted row, or the row was deleted in the process of editing this document. Now when we look at that hierarchical comparison unit list, we see that we have a table, we have a row, we have a cell, we have a paragraph. Then within the paragraph we have words, within the words we have atoms. We can see the SHA-1 hashes for everything, and now we can see these GUID identifiers over here, and we can see that here is the GUID identifier for the first row, and that's different from the GUID identifier for the second row. And that way, when we reassemble this entire document, we can use these GUID identifiers to correlate the tables and rows and cells and paragraphs as we're putting these content atoms back together into an entire document. This figures into the algorithm in an interesting way that I'm going to discuss later on. I'll now delete this debugging information. Once we have called getComparisonUnitList for both the before and after document, we are now ready to actually create a new document that contains the changes between those two comparison unit lists. That's what this apply changes method does. What it does is it takes a copy of the after document, assembles a new main document part, and injects this new main document part into the after document, and then that is our new document that has the appropriate changes. It will have tracked revisions that mark everything that changed between these two documents. Let's go in and take a look at this algorithm. I told you we were going to get geeky in this, so we're going to get even more geeky here. One of the things that I did is that at various places throughout the code, there are places where it dumps out entire lists of comparison units and so on. This enabled me to debug this algorithm, to develop it and debug it. This code is always not run by default because it tests against this s under false variable. This s under false variable is just a variable that is set to false, and it can be set to s under true if we want to use it. The good thing about using this approach is that it enables us to find out all the places that are compiled in by, here I have this s under true, I can go to s under true, I press shift F12 and it will show me all the places where the debugging code is going to be run in the upcoming test run. We're going to look at now the two comparison units for the modified documents that we're going to be comparing. Let's take a look at this in Notepad. I'll go back to that CA001 example. This contains simply a deleted word in the after document. This will enable us to more easily watch the algorithm as it goes through the process of determining the deltas between these two documents. And here we now see comparison unit list 1 contains our paragraph and then contains the atoms. Video provides a powerful way to help you prove your point. And here is the second document, and it has that word provides deleted. It has video, a powerful way to help you prove your point. So we're looking at a very simple example here. It's worthwhile to walk through the algorithm on a simple example before we start diving into how it handles extremely complicated, more technically challenging situations. I'll set a breakpoint there. I'll now close Notepad++ so the code will hit our breakpoint. We're now going to go into the LCS method, and this is the method that implements a highly modified variation on the longest common subsequence algorithm. This is a highly modified variation on it because it takes into consideration tables, rows, and cells so that it can find out whether a table has been deleted, whether a row has been deleted or inserted, and it can find specific deltas in cells, and it will never set as equivalent contents in one cell to another cell. A cell can only be equivalent to contents in its own cell, corresponding cell in the other document. I think before going into the LCS algorithm, let's set another breakpoint right here and see the results of this algorithm. I'll press F5. Now we're looking at the results of running the LCS algorithm. What we can see is there is a correlated sequence that contains a correlated item where everything was equal, and this is the first word, video. We then see a correlated sequence where the correlation status is deleted, and the correlation status here is for space provides. It's this content right here. By the way, we don't need to pay attention right now to this correlation status. That comes into play later. That we have noted that the correlated sequence is deleted will eventually cause in the algorithm these correlation statuses to change from equal to deleted. And then we can find here the rest of the document, which is all equal. So the question is, how did we get from the initial set of comparison units in this hierarchical form to this form? This is what the algorithm is all about. The first thing that the LCS algorithm does is it uses a really simple optimization, which is to find any common content at the beginning and end of the sequence. When an author changes a document, very often they leave lots of things at the beginning of the document the same, and they leave lots of things at the end of the document the same. If we can quickly identify those regions that are equivalent at the beginning and end of a document, then we can save time before we actually get into the actual LCS algorithm. The LCS algorithm is a fairly time-intensive process because it needs to go through and find the longest common subsequence wherever it may occur in those two sequences. And this is an operation that is O of n over 2 squared, or effectively O of n squared. So it's a time-consuming operation. By first finding common sequences at the beginning and end of a particular region, we eliminate the regions that we find from the actual LCS algorithm, which is O of n squared, and this operation is just O of n. It depends simply on how many paragraphs that we find at the beginning and end of the document that are equivalent. I started using this approach when my initial implementation of the LCS algorithm proved to be too slow. So this was an optimization to find the common at the beginning and end of any particular unknown region. Note that finding the common stuff at the beginning and end of a particular unknown region, this happens all the way through the algorithm. This will also happen on a sub-region that we happen to find in the document. After we find the common content at the beginning and end, then here is the actual LCS algorithm. And as you might imagine, this algorithm iterates through every item in the left side of the content and goes through every item in the right side of the content and looks for items where the SHA hash is the same. At the end of this double loop here, which is the loop which is O of n squared, then we either have a longest common subsequence or we don't. We may not have a longest common subsequence. It's possible that there are no common subsequences in a particular list that we need to compare, but it's possible in most cases we will find something. When we find this something, there are a couple of interesting points about this algorithm. We never start a common section with a paragraph mark. This would mean that we're taking the last pilcrow of the previous paragraph, which was different, and including it in the content that follows, and that doesn't provide for good deltas between the documents. So we never start a common section with a paragraph mark. That's all that this does. Is if it finds that the common subsequence starts with a paragraph mark, it simply pushes forward the start of that common subsequence so it doesn't include the paragraph mark. That makes the algorithm more in the way that we expect. Another thing that this algorithm does is if the longest common subsequence is just a space, then we don't call that as equivalent per this algorithm. We need something longer than just a space to be common before we start saying that two subsequences are equivalent. This next part of the algorithm is kind of interesting in that I developed this after I didn't like the initial result I was getting out of the algorithm. The key point about this section is that if the longest common subsequence is less than 15% of the whole subsequence, then forget it. Don't call it common. We want to keep finding reasonably sized chunks that are different. We don't want to find something and says this word was inserted and deleted, and the next word was inserted and deleted, and the third word was inserted and deleted. What we want to do is we want to see the first three words are inserted and the last three words are deleted, and that's what this optimization does. You can play around with this 15% if you want to have it report different granularity in your documents. This is a value that is set in the detail threshold field in the settings that you pass into this module. And you can change this to 20% or 10% and see what results you get if you want to see any difference in the granularity in how it reports deltas between the two documents. The next thing that this algorithm does is if it doesn't find any common subsequence, then what it does is it flattens that particular range and again tries to find common subsequences. So for instance, we have two paragraphs and the two paragraphs are different, and the algorithm says no, they're different, we have no common subsequences. So what we then do is flatten those paragraphs to their words. And then we can find the common subsequences for those two collections of words. And this is how this algorithm delves into each paragraph and reports the differences at the word level. If it finds that two paragraphs are different, but they're at the same location in the document, then they will get flattened and we will get the differences at the word level. This algorithm has some other interesting characteristics, and I'm going to talk about those in just a bit, but I think it's now worthwhile to watch this algorithm go iteratively through the process of determining the common subsequences for our very simple example. I had told you that this was an iterative process, and this while loop here in the LCS algorithm, this is the iteration that is the key part of the iterative process. And one of the things about this code is at the very beginning of it, it has the opportunity to dump out the correlated sequences at that point in time in the iterative process. So let's change this to S true, and we'll set a breakpoint here. We're going to run the algorithm and we're going to see the comparison unit list as it goes through the algorithm and determines the deltas. Now in this super simple example, it's only going to go through in kind of a simple way. I'm going to run again on our simple example that has simply a deleted word. And here we are looking at the correlated sequence at the very beginning of the operation of the algorithm, and all we have is one correlated sequence of unknown. And we have the comparison unit list 1. This is the before document. It has a paragraph in it. And we have comparison unit 2. This is the after document, and it also has a single paragraph in it. First thing it does is it finds an unknown correlated sequence. And in this case, it's the entire document. It's going to go into this algorithm and find common subsequences at the beginning and end. Now, because we had one paragraph only in both documents and that one paragraph had changed, it found no common subsequences at the beginning and end. And this is correct. So when it didn't find anything common at the beginning and end, it goes in to do the actual LCS algorithm. I'll run to cursor, and now we'll look and see the longest common subsequence is 0, and the current I1 and current I2 is -1. And this is correct. It didn't find via the LCS algorithm any longest common subsequences. It'll do some various checks and adjustments. Those are only applicable in the cases where it actually found common subsequences. In the case where it didn't find a common subsequence, they don't do anything. So we want to run to this location. This location, it's going to again look at certain situations, but the relevant thing is here it's going to determine that the left side, in other words, the before document contains only paragraphs and tables, and that is true. It contains only a single paragraph, and it's going to determine if the right side contained only paragraphs and tables, and that is also true because the right side contained only a single paragraph. So what this algorithm does is it flattens those paragraphs and creates a new unknown correlated sequence to take the place of the existing unknown correlated sequence that we're working on. And back in the LCS method, what it's going to do is it gets back this new sequence and it runs this little teeny bit of code that simply finds the existing unknown correlated sequence and replaces it with everything that we returned from the do LCS algorithm method. And so when I run it again, it's going to come back up here, and again it's going to open Notepad and show us what the correlated sequence looks like at this point in time. So I'll press F5, and now we're looking at what the correlated sequences look like at this point in the algorithm. Here we can see the paragraph is gone. Now what we're looking at is a correlated sequence where the left side is a list of words and the right side is a list of words. And this is going to get more interesting. In fact, this now is going to cause the algorithm that looks for common content at the beginning and end of a correlated sequence, and it's going to find that content. It's going to find that video is the same before, and it's going to find the other content that is the same after. So it found that correlated sequence. Now we're going to go into find common at beginning and end. First of all, the length to compare is the minimum of these two. We never need to compare more than the minimum of two comparison unit arrays. So in this case, we have to compare up to 21. And here's a nice little link expression that zips together the beginning of the two comparison unit lists and counts the number of items where the SHA1 hash is equivalent. And we're going to get a number here. What is the number? We're going to get 2, which is the video and the space. Those are common comparison units at the beginning of those correlated units. Those are common at the beginning of the two lists of content that we're comparing. And we look to see if the amount of content that we found falls below the detail threshold, and if we do, we get rid of it. And in this particular case, it did. Later on, we're actually going to be able to find that common subsequence per this algorithm. It's going to count common at the end. Common at the end is going to be 20. It found 20 comparison units at the end that are equivalent. It looks to see if we started with a paragraph mark, and it's going to say no, this common subsequence did not start with a paragraph mark, so we can skip the code that gets rid of that starting paragraph mark. So at this point in time per the algorithm, we didn't find anything at the beginning, but we did find 20 units at the end. So when we resolve this, it's going to say what we're going to do is we're going to create an unknown correlated sequence for all the content that came before what we found that was common. So we have an unknown correlated sequence that contains video provides in one case, and in another case it'll just contain video. And count common at end is not 0, so we'll create a correlated sequence where this content is equal. I'm going to press F5 now, and it's going to go back up to the beginning of the loop and open Notepad++ with the current state of our affairs. So here we can see, yes, we have an unknown correlated sequence that has video provides on one side and it has video on the other side of the comparison, and everything else down here it says this is all equal, so we're good to go on that. Now again we're going to find common at beginning and end, and this time it found common content. It's the word video. It's not going to find anything at the end of this one. That's going to be 0. So we have common at the beginning. We'll create a correlated sequence where the correlation status is set to equal. And then it's going to notice something else. It's going to notice that on the right-hand side, the common subsequence that we found starts at the very beginning of the correlated sequence. So that means there's content on the left that isn't on the right, so therefore it can create a correlated sequence with deleted content right here. Now when I run, we're going to again get to the beginning of our iterative loop and dump out the state of things. And now we see, yes, we have a correlated sequence of equal, we have a correlated sequence of deleted, and we have a correlated sequence of equal. So now when it looks for the first unknown correlated sequence, it's not going to find one, and that means that the algorithm is done. Now the next thing the algorithm does is it does a little bit of fix-up so that when we move a deleted row from the before document to the after document, it has the revision tracking markup in the row properties, so that row is noted as deleted. We're not actually dealing with rows right now as we're going through this algorithm, so let's just skip that code for now. I'll run to cursor. The transform to take a list of content atoms and assemble an entirely new document with appropriate revision tracking marks needs to have a flattened version of the comparison units. We no longer care about the groups and the words in the comparison units. We just want the atoms. The atoms have enough information to assemble the entire document. We needed the words and groups in the process of determining the deltas between the documents, but now that we've determined the delta between the documents, we don't care about them anymore. So this code here creates a new list of comparison unit atoms where it's all flattened out and contains just the information that we need to reassemble the document with appropriate revision tracking. This is where the status in the comparison unit atom gets changed appropriately to correlation status deleted or correlation status inserted. Let's set a breakpoint right here. And let's take a look at what the list of comparison unit atoms looks like after we've flattened them. I'll press F5. And now we can see the list of comparison unit atoms, and we can now see that the comparison unit atoms for that deleted word now has the correlation status of deleted, and everything else is equal. The next bit of code is pretty interesting here. I want to point something out about this dump here, which is we can look up here and we can see the ID for the paragraph in the after document. Up here is this 3475, etc. And we can see the ID for the deleted content in that same paragraph in the before document. Is this D921. We want to put this deleted content into this paragraph that has the ID of 3475. So that's what this next code here does, is it goes through all the correlated sequences where the status is equal and goes into every item there that has a unique ID and sets the unique ID in the before document equal to the unique ID in the after document. Therefore, when we coalesce all of these comparison unit atoms into an XML tree, the deleted content will get put into the right paragraph. Let's look at this after going through that algorithm. I'll change that to S true, set my breakpoint here, and close Notepad and run. And now Notepad comes up again with our list of comparison unit atoms. And look over here, the ID for the paragraph for this deleted content is set to the same ID as the ID in the new document, and this will cause all of this deleted content to be put into the right place in the newly assembled document. It took a fair amount of time for me to work out the best way to make this work. I don't want to bore you with all of the details of the wrong paths I went down when putting together this algorithm. This turns out to work very nicely. It doesn't matter that we set those GUID IDs in the previous document. Effectively, we're done with them at that point in time. We need to use them now for assembling the new document. So that's how this works, is it sets the IDs in the old document for all pieces of content that are equal. It sets those IDs to the same IDs as in the after document, and therefore everything gets put together into the right paragraphs and the right rows and the right cells. And finally, we're at the point in the algorithm where we can produce a new X document from this correlated sequence. Let's take a look at this one. This method calls this coalesce recurse, which is a pure functional transform that takes lists of comparison unit atoms and produces X elements as appropriate from those lists. This part of the algorithm, it has a different signature than what we normally find in a recursive pure functional transform, because we iteratively pass in lists and sublists as we build up the tree. This is not the normal type of pattern that we find in these types of transforms, but what this means is that we can have this coalesce recurse method. It's not a huge method, it's probably 100 lines or so, and it can build up the complete XML tree from that list of comparison unit atoms. I'll press F10 so that we get past producing a new XDoc from correlated sequence. And here we can see a very nice OpenXML document, and it has all of the deleted and inserted content in this document with appropriate markup. I can see that as I have recorded this, I have neglected to add the code to coalesce all of these runs with the same formatting into a single run. We're now free to do that. I'll add that into this algorithm in the next day or so, but it's really irrelevant as far as the explanation of this algorithm. It doesn't matter with regards to valid OpenXML content whether we have all of these runs as runs of a single character or not. And then there's a little bit of cleanup following that, and then we're done. The cleanup has to do with we leave some OpenXML Power Tools markup in that document. Mainly I left it there for debugging purposes. Probably get rid of that markup in the final version of this module. There's also the issue that it's more convenient if we move the very last section properties as a child of the body element into the child of the paragraph properties of the last paragraph of the section. Now, that's different from the standard. The standard says that the last section properties should be a child of the body, but we put it in as a child of the paragraph properties to make our code more general. And then when we're all done, we take it out of that last paragraph and again put it back in as the last child element of the body element. If you are going to implement something along these lines, well, it's going to require a bit of study. It's not a simple algorithm. That operation that I discussed, where we looked at a paragraph and determined that there were no common sequences of the paragraph, so then we flattened it to the word level, that same operation also takes place for tables. If we are looking at a table and we can see that the table is different and that's the only thing in the correlated sequence, the next thing it does is flatten that table to rows, and it then looks for common rows in those two tables. It'll mark such common rows as equal, and if it finds rows that are not common, then it can either mark them as inserted or deleted, or if it can't do that, then it'll flatten the rows to cells and find common content in the cells. There are tests that we can do with respect to the rigorousness of our idea here of content atoms of a document. I have plans to implement these as opportunities present themselves, as I have enough time. For instance, after accepting tracked revisions on the newly produced document, it should have the exact same number of content atoms as the after document. If this assertion holds true for all kinds of varieties of documents, then we can feel confident in the quality of this iterative transform. In other words, we go through this process and we have exactly the same number of content atoms in the document that we produce with revision tracking as in the after document. I can implement this test easily enough by using the revision acceptor module, and then I can test it. Another thing that would be interesting in the future, as soon as I have good code for rejecting tracked revisions, is I could reject tracked revisions in that document. I could then count the number of comparison unit atoms in that document, and that should be exactly the same as the number of content atoms in the before document in this process. This was a super interesting problem to solve. I actually went through 4 iterations of the code. I first implemented it without taking into consideration tables and rows and cells. I had a far simpler algorithm at that time and far simpler data structures, and that didn't work at all. As soon as you match up and compare content and determine that content, for instance, in 2 cells are equivalent, but you shouldn't be finding that content as equivalent, then the whole operation kind of breaks down and you produce odd-looking tables and so on. So I realized that the LCS algorithm itself has to be aware of tables, and it has to be aware of rows, and it has to be aware of cells. And that's when I came up with this class hierarchy with the abstract base class of comparison unit, and then we have the comparison unit atom, comparison unit word, and comparison unit group that the LCS algorithm actually deals with. Well, if you've made it to the end of this screencast, you're probably one of very few who have done so. This screencast is not for everyone, but it is an important screencast for those people who need this screencast. And in particular, this screencast is going to be very important to me in about 2 or 3 years when we want to enhance or do something to this algorithm. And I won't remember it, so I can watch this screencast and remember how this particular algorithm works. I know it's pretty geeky. If you haven't written or reviewed code like this in the past, it'll probably take a bit of study to understand exactly how this algorithm works, but this should give you the general drift of how it works. That's all I'm going to cover, and that was more than enough. See you later.